Thank you to the organizers for inviting me. So I have three starting comments to make. The first is that Tamada was furious that I insisted on us talking about this material when the analysis in the nonlinear cases is completely open. But, so sorry. But I figure, you know, okay, we always have to ask, well, what are you working on? What stuff is coming up? And so you don't need to ask. This is what I'm working on, and I don't really know how to solve it, but there's a lot of, I think there's a lot of mathematics that one has to understand in order to attack this work, okay? So first I wanted to ask for people to hand in their homeworks. You were given an assignment earlier today. Pass them down. I'm kidding. But so there were two problems. One was to carry out the derivation of the space-time correlation function in the case of periodic boundary conditions. And there was another problem which was to understand the error. Okay, so up at the top of the screen is from Tamada's slides is the space-time correlation function, the momentum correlation function. It's a finite sum. M runs from 0 to capital N. And so, of course, it's clearly a Riemann sum, and so it should converge to the integral, and that's what's written down below. And so the second problem was to understand what's the error term. So what do you think the error term is? Anybody want to hazard a guess? Is it 1 over n to the power 1, or is it 1 over n to the power 2? Or is it really 1 over n to the power infinity? Okay, so those are the two things that well, we kind of thought would be fun things to think about, and I'd like to show you why. Okay, so this is just repeating. We have a Hamiltonian system with random initial data, and so at the very top is the type of Hamiltonian that we're considering. And I'm restricting myself to the linear case for now. And the Gibbs measure is how we're sampling initial data. So it's random initial data. You're picking initial positions and velocities according to this probability measure. And n is supposed to be large, and actually beta is supposed to be large. And then you want to see how it is the solution at time t, how is it correlated to the solution at time 0, and it's space-time. So solution at site j at time t, how is that correlated to solution at site middle of the chain at time 0? That's the question, okay? And that's what's written there. SQQ is the position correlation function, okay? SPP is with momentums, the velocities. So here is a plot of the position correlation function at time 0 in the linear case, and also at time 5 pi, okay? And what you see is that at time 0, there is a locally concentrated function. The first thing is to realize that you're only going to see propagating waves if that's the starting point, if you have something which is nearly delta correlated at t equals 0. Okay, and then, well, then it begins propagating, two waves moving in opposite directions, okay? This happens to be 201 particles, okay? Let me scroll forward. So Tamada showed you numerical experiments, and I think that the largest number of particles they considered was 8,000 particles, and the largest number of samples that they carried out was 1 million samples. So the reason for the second question is to ask, is what they're seeing at all relevant? Is it anything to do with n going to infinity or not? Okay? So if you take 1 million samples, how close do you get to the expectation value? Usually it goes down like the square root of the number of samples. So if someone has made their computer run 1 million experiments, they get 3 digits of accuracy. That's it. And that probably took a week, 2 weeks on their computers. Okay. So if n is 1,000 and the error goes down algebraically in n, then you might not have any relevant information about the large n limit, unless you happen to know that the error in n goes down much faster. So at least in the linear case, there's consistency. And that's why it's important, that's why this question was important. Do you really know that the error goes down exponentially? And if you do, then you don't need 1,000 particles. You can just take 100 particles, because e to the negative 100 is small. Okay? And the second thing is, the second reason for the second question is, well, in the experiments that we saw earlier today, they were considering the total lattice with periodic boundary conditions. And Tamada showed us how to solve the total lattice with periodic boundary conditions, but that's actually harder to carry out analysis on the periodic total lattice than it is on the other boundary conditioned total lattice. It's called the open lattice. And so does what you observe depend on the boundary conditions? And that's why the second question was, or maybe it's called the first question. Maybe that's why we were wondering about that, because you don't want to be studying a problem where the boundary condition has an effect. So in the linear case only, you can really prove that you get the same formula, whether the boundary conditions are periodic or Dirichlet boundary condition. That's comforting, at least, because if you read the papers that Tamada was referencing, there is no effort to explain why the simulations are justified. It's just, let's do these experiments and enjoy them. Borderline on engineering. Okay? So, well, I'm disappointed at the class not having done their homework. But maybe that's the first thing to talk about briefly, because it's kind of fun to see why it's exponential. People probably have a guess why it's exponentially convergent. Anybody? So let me try to find the right slide. Yeah. Is that the right slide? Oh, sorry, I gotta go to the other. There it is. Turns out that that's a trapezoidal approximation to the integral. Okay, and if you have a periodic function and you consider the trapezoidal approximation to its integral over the period domain, the convergence is exponential. Okay, so anybody seen that before?
No, I didn't know that.
So great, because I thought I would just explain that quickly. Okay, so when you look at that, you see the grid points are from like 0 to 1. And the periodicity of the function that you're looking at happens to be from 0 to 2, so there's a little bit of massaging to turn it into a series that goes from 0 to 2, but you can make that work out. So I want to just explain, if I have a, so let's see, suppose f is analytic. Okay. So the trapezoidal approximation to an analytic function, so to an integral of an analytic function over a disk, over a circle, is just this. 2 pi I. Okay? K goes from 1 to n. So we always teach our calculus students that the trapezoidal rule has this 1/2 weight on the boundary terms, but if you have a periodic function and you do it right, it's exactly this sum once you put it on the unit circle. So that's a piece of luck. Okay? Okay. And the integral we're trying to approximate is just this on the boundary of the disk of radius 1, f of z dz divided by z. Okay, that, it turns out, is what this series converges to, okay? So I want to assume that it's, I'm not worried about domains of analyticity. It's analytic in a big disk, bigger than the circle of radius 1, okay? So then In is 2 pi over n. And then it's a sum of Cj, sorry. It's a sum, k goes from 1 to n. And now I replace f by its Taylor series, okay? Centered at 0. So j goes from 1 to infinity, 0 to infinity, sorry. Cj, and then, so the zk's are the points that I've discretized, okay? So Cj's are the Taylor coefficients. There's a good formula for those, right? So those are Taylor coefficients. Which I, of course, didn't write down. Oh, no, there they are. So it's 1 over 2 pi integral f of e to the I theta, e to the negative I j theta d theta. So the first term, well, so C0 is the integral in question, right? I is C0. If I did it right, okay? So the series in question is just rewritten in this way, and let's interchange orders of integration, of summation. Right? And then it's zk. So I should write it out. E to the, well, e to the I 2 pi I k over n to the power j. Okay? So if j is a multiple of capital N, then this series is just capital N. I must be missing some prefactor. Yeah, 2 pi over n, sorry. So if j is a multiple of n, then the series is just capital N. And if j is not a multiple of n, the series is 0. Okay, by aliasing or whatever you want to call it. So this series is really 2 pi over n, sorry. summation. J goes from 0 to infinity. Actually, I could call it J is equal to L times N. And L goes from 0 to infinity, right? So C, L, N, and then there's just an N that sits here. Okay? So what is that? 2 pi C0, that's the integral in question, plus the sum, L goes from 1 to infinity, of C, L, N, right? Probably drop the 2 pi again. Okay, so when J is 0, I've got the integral in question, and so if I can control all the other terms, I'm in business, and that's where the analyticity in a slightly larger disk is relevant, okay? So if I know that this is analytic in a slightly larger disk, I can write down a formula for C1, C2, and C3 as an integral over a slightly larger disk, and I have a 1 over R to a power L times N, okay? So CL times N is, so 1 over 2 pi I integral over the slightly larger disk, the disk boundary of a disk of radius R with R bigger than 1, F of Z over Z to the Ln plus 1 probably dz. And you can control that by a C over R to the power capital N for all L. That gives exponential convergence, okay? So that's a fun fact. Whenever you have a series, if you can turn it into a trapezoidal rule and the function's periodic, you get rapid convergence. If it's analytic, you get exponential convergence. If it is smooth, then of course you can get any order you want, but you got to do some approximation theory. So you're looking at this and you might be saying, well, hold on, that function's not analytic. Once I map into this, you know, I have to replace e to the I theta. Okay, cosine pi s becomes z plus z to the negative 1, and so there's a pole floating around. You can extend what I just did to the case of analyticity in an annulus. You got the, instead of using a Taylor series, you use the, what's it called, the McLaughlin, no, the Laurent series. And part of it you extend outside and part of it you extend inside, and it works, okay? So that's where this order n to the negative infinity comes from. Good? Okay. Okay. So I'll just show you what that means. So here is, the left-hand side is a plot using Mathematica of the integral. And the right-hand side is a plot of the series at the top. So they're both exact objects. The right-hand side is discrete. The left-hand side is in the continuous limit. And here's the error between them. Okay, now you can't see it, but the scale is 10 to the negative open solid, it's 10 to the negative solid disk. No, it's 10 to the negative 9, or 8, 10 to the negative 8. Okay? So with 100 particles, you have error 10 to the negative 8. That's really showing exponential convergence, okay? And that means that if you want to do simulations, you can probably get by with 200 particles instead of 8,000 particles, as long as when you are studying the simulations that things are not getting near the boundary. Once they get near the boundary, all hell breaks loose. Okay? Good? And then the left-hand side is the same plot as before, so it's the sum itself. And then the right-hand side is I've used 10, so 10 to the 6th, 1 million samples, and solved the linear ODE system on the computer. Instead of, well, okay, so yeah, I did it. And the error is 10 to the negative 3. Okay, so that tells you that, all right, if you want to do Monte Carlo simulation and get 3 digits of accuracy, you need to take, I don't know, maybe 100 particles, but you are going to need a million simulations. So that's where all the work is, making sure your code is efficient enough that it will solve the ODEs, you know, so you can repeat it a million times. It's weird, right? But I think it's useful to think about these things if you're going to start embarking on computational simulations to try to understand phenomena. Okay, so I remind us that what we saw earlier today from Tamada was that there's a claim that those traveling peaks are described by some kind of a KPZ universality guess. And only in the case of integrable systems, of non-integrable systems. And okay, let me just scroll forward. These are the experiments again, but let me scroll forward just to pose the question. So these are all supposed to us to sort of stare at them and enjoy. Oh yes, there are traveling peaks. Okay. So maybe these two are interesting. The first one is 101 particles with 100,000 samples. Okay, and the time at the top is pi, 2 pi, 3 pi, 4 pi, and 5 pi. So you see traveling peaks. And the two curves that you see are the orange is Toda, and the blue is the harmonic chain. These are, again, the space-time correlation functions plotted at 5 different times. And beta happens to be 1. So capital T is the temperature and beta is 1 over T. And then I just took beta as 100, and this is what you see instead. So it's same Toda lattice, but just with beta very large, you're sampling closer to the ground state of this Hamiltonian. So let me tell you, I'm cheating a little bit. In both experiments, I'm using the harmonic oscillator Hamiltonian to generate the random variables. Okay, so I'm not using the Hamiltonian of Toda. If you're a statistical mechanician, you might say, well, what are you doing? But then, you know, okay, with an integrable system, it's not going to sample all the phase space anyway, so we don't really need to worry about using the invariant measure to generate random initial data. But anyway, the interesting thing is, as I crank up beta, I'm solving Toda, but the initial data is nearer and nearer to the ground state, which is a constant of motion of Toda. And so the solution actually is behaving more and more like the linear case. It would be really great to prove something about that. Okay, so the next question is, what is the simplest explanation of this traveling pulse? I'm going to answer it, but I thought I'd just go slowly. So yeah, I'm asking you guys. So I have a simple explanation for traveling pulse, but it just struck me when reading these works that no one's explaining sort of from some fundamental level why there are traveling waves. You kind of know why. You got a system of chains.
Well, why it's traveling ballistically?
Sure, both that too. Is it traveling ballistically? That's another one, right? Yeah.
Yeah, well, because there are these action angle variables, and basically they travel.
That's an explanation for why there's a traveling wave.
Yeah.
Okay. All right.
So when you got times there are like 3 particles, you would expect that your again the perturbation they're ballistic. So you have like a bunch of 3 particles in the dice, and they carry your whatever perturbation.
Uh-huh. Yeah. So bear with me. Yeah, the first thing is in the case of the linear springs, the first statement is that this space-time correlation function still solves a discrete wave equation. So I'm going to use the letter S. It could be space, position, position, or momentum, momentum, doesn't matter. But it will solve this equation, d2 s, let's say, k by dt squared is equal to nu times discrete Laplacian of s, okay, at position k, minus 2 mu times s. Okay, so that's the first statement is, oh, it's linear, so it still solves, turns out it still solves a discrete harmonic oscillator system. And the initial data, you know, I plotted it, looks like this. So maybe there's some solution procedure that could really elucidate two traveling peaks. But you saw the formula. It's not exactly pretty. And even after taking a limit, there's an integral representation. So you can extract the traveling wave from the integral representation. But before doing that, I'll just point out, here's another fun calculation that you can do, or we can do, okay? So I want to consider another scaling limit. So the parameter mu, which, okay, if you remember, the parameter mu was part of the Hamiltonian. It's the coefficient of the r squared. The parameter mu is going to go to 0. And the temperature, beta, is going to go to infinity, okay? So that beta times root mu converges to some number eta, which is non-zero. Okay. And then, maybe I should point that out too. In this integral that we just derived, at the bottom of the screen, alpha is an integer. Right? So it's still the infinite particle limit, but it's an infinite number of particles, and its index alpha is the position of the particle. Okay. So I want to rescale alpha by setting alpha as x, a continuous variable x divided by root mu, and also rescale time so that t is going to be tau divided by root mu. Okay. So I guess I'm pretending to be an applied mathematician to set up a scaling limit to see the simplest possible explanation for this traveling wave phenomena, okay? I guess I'm going to erase this. Looks like there'll be some jazz tonight. I cooked that up so that the equation at the top just becomes the wave equation, except that if you work it out, you wind up getting d tau tau now, minus nu dxx on s plus mu, I guess it's going to be, let me remember, plus 2 s equals 0. Okay, so it's a wave equation with this annoying term in it. Okay, and of course, if you check it, this integral solves that equation. Okay. So that's sort of, I feel this is a nice explanation for having traveling waves. Because I'm claiming that somehow we all know that equation has traveling waves. But I went and checked, actually, And by just plotting this function,
So alpha is x, yes?
alpha becomes x in the scaling limit, yeah. And let me see if I can just show you the picture of that. Can you see that? Okay, maybe this is that's the initial data. Okay, that's a plot of the initial data. And that's a plot at time 5, and time 10, and at time 20. And you can't see it, but actually it's not a fixed traveling wave. It is a more complicated thing. The peak is dropping as time evolves, and it's moving out at a constant velocity, but the peak is dropping. And you can even see it's even weirder. The peak is dropping, and there are more oscillations that are kicking in as well. That's a zoom in on the edge at time 20, and that's a plot at time 40. So, okay. So that begs the question, what is going on? Okay. It begs the question, what's going on? And I want to just next point out that everything can be understood from this integral. So if you do that collection of transformations to that integral, what you get is a function of x and tau that looks like this. There's some 1 over some 2 nu, an integral from 0 to infinity, cosine of pi s, cosine, I'll probably get this wrong, but t square root of some constant times s squared plus another constant. Okay. Divided by so I don't remember what the constants are, but they're just numbers. It might depend upon eta still, and nu, but they're just numbers. All right, so that's actually a solution of this equation. And in order to see this kind of propagating and dropping wave, there's one technique at our disposal, which is steepest descent analysis of this integral. And so it's Brian Ryder moments ago referred to the vanilla steepest descent method as the one in infinite dimensions. So this is somehow even simpler. This is like air and water steepest descent method. But so, okay, it still looks ugly. It's got cosines and cosines. But basically you can study this by looking at things like the real part of an integral like this. Cosine pi s, e to the I times t square root number sign s squared plus triangle minus pi times s. Pi, there's an x missing, pi xs, sorry. Pi times x times s. Divided by whatever this thing is downstairs, number sign s squared plus triangle. Okay? 0 to infinity. So steepest descent method applied to this integral shows decay of rate 1 over square root of t. And it shows a propagation speed and sort of a maximum speed of propagation as, okay, now I'm forgetting it. I just did the calculation, but think it's the square root of nu. But okay, I'm not remembering because I need to know the number sign and the triangle to get it right. But so calculation is explicit. You just do it. But what you find out is that it's not going down like 1 over t. It happens to be going down at a rate that's 1 over root t because of standard steepest descent analysis. And there's lots of oscillations. So I think this explains why there are traveling wave solutions, which from the starting point, you see them and people talk about them, but there's a overlooked question: where is the traveling wave? What's the origin of the phenomena of the traveling wave? And so there's simple sort of applied mathematical rescalings to explain it. But along the way, what you realize is that equation, it's dispersive. Waves of different frequencies travel at different speeds. And okay, you know that actually because when you look at this integral, you realize, oh, it's got a dispersion relation. You have to compute what the dispersion relation is, and that's what gives you the calculation I'm just describing. Okay, so I would say then that dispersion is a phenomena which has been overlooked by this community of people doing computations. And the dispersive phenomena is not only present in integrable cases, it's present in many cases. And it doesn't mean that the claims are wrong, it just means that there are interesting calculations that need to be done, even in the integrable cases, even in the linear cases. Okay?
Yeah, sorry, but I'll disagree. Does it agree with the experiment or not?
It does not agree with the experiments that we saw, but the experiments that we saw were for a periodic total lattice. Okay, and it's possible that somehow that lattice is just missing all dispersion, but I don't understand why this 1 over root t decay is not present there. It's also possible that well, I've made a calculational mistake. That's more likely than anything else. Okay? So I should give this as an exercise, right? Derive this properly with the correct constant number sign and delta, and then apply steepest descent method. Okay, and see if you can explain this picture that I've produced with Mathematica. Okay? Explain this collection of pictures by steepest descent analysis. All right, so that's the first, I would say that's sort of the first explanation for the traveling wave phenomena, all right? And it's take scaling limit of the linear system so that you're looking at something that's solving a PDE, and in that scaling limit, the integral simplifies. And then that simplified integral you can calculate. You can calculate things. Okay? There are parameter games still to be played. Okay? So let me find the... So there are parameter games to be played, and maybe, is it up there? Yeah, so you see I skipped this earlier because I thought it would be better to come back and say it now, but there's a mu tilde and a mu up there on the screen, all right? And you can choose the system of chains with one choice of mu tilde and the Gibbs measure with another choice of mu, and study the behavior of this space-time correlation function with two different choices of mu. And in particular, you can pick mu tilde to be 0 if you want, right? So what is the physical meaning of the mu tilde? You've got a bunch of particles, right? They're connected by springs, and each one feels the presence of its two neighbors. And if that mu tilde is non-zero, it is in its own potential well. So it's got this mixture of competing forces, one from the nearest neighbor, one from the other side's neighbor, and also itself. And you can tune that and make it completely independent of the choice of mu that you put into the Gibbs measure. You need it there in the Gibbs measure so that you have a finite, your measure's finite. You need mu non-zero in the Gibbs measure, but you don't need the parameter, you don't need that confining term in the actual equations of motion. So that means you can play around with mu versus mu tilde. And you can take these crazy scaling limits. Okay? Okay, so that's probably a good place to stop, right?
5 to 10 minutes.
Oh, all right, well, let's see. Let me take a look and see what we can do next. Okay. All right, this is all covered, good. Good, so let me go back to this then. Okay, so the next thing is to go back to the lattice without taking this crazy scaling limit and ask what. So with this formula here is now the 2-point space-time correlation function in a discrete lattice with an infinite number of particles. Okay, and so the next thing I can start setting it up and then stop. The next question is, what kind of traveling wave phenomena are there in this formula, in the discrete lattice? Okay, so maybe I'll just write down a homework assignment. So let's go SPP. So the problem is to, derive the formula for SPP instead of SQQ because it's a little bit simpler. It has no denominator in it. And then compute the long-time asymptotics. You'll have to let alpha scale with t. And the challenge is to identify all of the scaling exponents in that case. Okay, and I guess I would like to suggest taking mu tilde is 0 and mu equals mu positive. Okay. So mu tilde is the coefficient in the Hamiltonian that describes the equations of motion, and mu is the coefficient in the Gibbs measure. And I'm suggesting take them differently and then identify there's 2 different scaling exponents that are relevant. And then, okay, just like the previous homework assignment, we'll just do it next time. Okay? But it's fun. I mean, give it a try. All right, thanks.
Thank you very much. Are there any questions, comments, solutions to the homework?
Need coffee? Oh.
So this portion is basically just a relativistic cohesive particle, right?
Like what, the equation?
Yes, so it's an environment with finite mass, which means that the propagator is basically some McLaughlin function.
Uh-huh. Okay.
Well, with the numerator maybe something. Just a comment.
True. I mean, it is, well, Sure, it's a special function of some kind, right? Yeah. Okay, thanks.
Yeah, maybe just another comment. Maybe the reason why for the harmonic oscillator you have this square root of t and not one over square root of t, and not, maybe the harmonic oscillator is too good.
Could be.
Because also, today someone mentioned the similar conjecture in quantum chaos. So for even in that realm, there are this conjecture about integrable billiards where you should observe Poisson, but this is a for generic billiards because for generic integrable system, because for instance for the quantum for the harmonic oscillator it's not true.
It could be
for some reasons.
Yeah, I mean, I'll just to annoy you, I'll point out these experiments, right? Let me go to them. So those are Toda and harmonic oscillator correlation functions on top of each other. Maybe time's not large enough, but so it's possible that time's not large enough, but you know, the phenomena is not terribly different between them. So I mean, I think once I get, instead of taking 100,000 samples, take 1,000,000 samples, there will be the same oscillations in the orange dots as there are in the blue dots, and those are dispersive ringing, right?
So different integrable system behaves statistically similarly. So
that's what I'm saying. Yeah.
The message.
Yeah.
And this is what actually, in this quantum chaos conjecture, this the quantum statistics of the eigenvalues. So if the systems are integrable, they are all Poisson.
Yes. So I should give away the ghost. There's when you do this calculation, you'll find a t to the negative 1/2 and a t to the negative 1/3 scaling in the linear case. So you know it's just that the zoo of different scalings is larger than what's been suggested by the preliminary studies that have been done. And I'm saying that because I don't think there's actually a distinction between, such a concrete distinction between integrable and non-integrable cases.
So what indeed we are, so just like you asked before for previous, so where are we going? So what we want to achieve? So what is, so there was some, so you are saying that there was something, some previous analysis which you're showing that not quite correct. Am I right?
There's no analysis in these cases. So I mean, where I would like to go is to take one of the total lattices, simplest possible case of analysis is probably the open lattice, and try to prove something about the space-time correlation function. I don't know how to do that right now, but that's the objective. And maybe it's ballistic scaling, maybe it's not. It's unclear. The computational things I've done suggest it's not going to be ballistic scaling, but that's still open. Yeah, that's sort of a long-term direction. Yeah, Guido.
But why you're saying that take the harmonic oscillator Hamiltonian to compute the Gibbs measure, so to have random initial data, is the same as taking the Hamiltonian of Toda, basically. I mean, it should be differences in picking random variable according to the harmonic oscillator and according to the Toda Hamiltonian, in principle at least. Why should be the same instead?
Well, probably it's not the same. I did this because it was easy. I mean, that's one statement, is that it's much easier to sample random variables from the Gibbs measure of the harmonic oscillator because they're Gaussians, and that's one of the reasons. if you take so which total lattice was I studying? I was studying the open total lattice case. Not periodic, but the open lattice case. And the Gibbs measure is not finite in that case. You have to do something drastic to it. So there's no invariant measure for the open total case. So there isn't one, doesn't matter which one you pick. I just picked the simplest one.
Any other questions?
Let's get coffee. Let's get coffee.
Yeah, there's coffee, right? Snack.